So good evening, welcome to this presentation. In this session, we'll talk about threat modeling. In particular, we'll be introducing a lightweight methodology to integrate threat modeling into the software development lifecycle. This methodology is designed with developers in mind to reduce reliance on security experts. I'm Andrea Scaduto, co-founder and director at Secure Flag. We help organizations in more than 30 countries with their secure coding training and threat modeling needs. My background is in offensive security, both as a security consultant working for organizations in many parts of the world, later as a VP of penetration testing for a large financial services firm here in London. During my career, I ran and managed many security activities, including penetration tests, code reviews, secure design architecture reviews, and I delivered many threat modeling sessions with development teams. I'm quite passionate about reducing the time developers spend on security work, so that time can be spent in creating value. And threat modeling is really a great activity to reduce rework because it allows to identify threats early in the development process and incorporate the right security controls from the start. And now I'm introducing you Andrew Hainault, who is also our host here at the Hainault building.
Oh, great, thank you, Andrea. I'm Andrew Hainault. I've been in IT and security for not 10 years, but more than 25 years, in fact, starting my career at Capgemini as a software engineer before moving into cybersecurity. And I've covered pretty much every domain along the way, working at ITC, Global Security, Gotham Digital Science, Strauss Friedberg, Aon, and now Level Blue, where I'm the EMEA lead for cybersecurity advisory. Over the years, I've witnessed and experienced a difficulty in getting software security initiatives adopted by development or DevOps teams, and threat modeling is a particular example of this. To that end, the approach we're presenting today is intended to encourage more development teams to implement threat modeling themselves by removing some of the friction involved. However, before we get onto threat modeling, I'm just going to take a couple of minutes to talk about Level Blue, who are co-sponsoring today's event with Secure Flag. Level Blue was formed last year after acquiring AT&T's cybersecurity division. Although it's new, its roots date back to AT&T's managed security services in the 1990s and Alien Vault's formation in 2007. Over the last 2 months, Level Blue first acquired Aon's cybersecurity consulting business, Strauss Friedberg, and then Trustwave. As a result of these acquisitions, Level Blue is now a 1 billion revenue company per year with about 2,000 people. Our core business consists of consulting services and managed security services. These include technical offerings such as network security, exposure management, detection and response, as well as more business-focused offerings such as cybersecurity assessment and strategy and GRC. There's plenty of information on the levelblue.com website, so please spend some time there to dive into details. We also have a number of strategic technology partnerships supporting our products and services, including Secure Flag, who've been working with us for, I think, 3 years. Most importantly, if they haven't all gone, there were some Level Blue water bottles at the end. So oh, yeah, right. Well, yeah, after the talk, help yourselves, because we've got, I think, ordered 200, so there are a few there. Right, first, let's talk about what threat modeling is, when to perform it, and why we do it. So threat modeling is a process designed to identify potential security threats and establish the appropriate security controls to mitigate those threats. The intention is to catch vulnerabilities early before they manifest as actual risks. When we're trying to anticipate potential vulnerabilities, ideally, threat modeling should be performed early in the SDLC when it's less expensive to make changes and often easier to incorporate security controls. We should also revisit the threat model every time that there are significant changes to the system or application. Threat modeling is a proactive security activity, meaning we're looking to identify security issues as early as we can. This helps us to manage our resources appropriately. In contrast, if we identify issues late in the SDLC, it's likely to be more expensive and time-consuming to remediate them. This helps us to manage our resources. Sorry, again. Lastly, by performing threat modeling, we can demonstrate due diligence and align with regulations such as DORA that stipulate risk management and resilience testing activities. We've seen the what, the when, and the why, so now let's look at the how. In other words, the process for traditional threat modeling. We start by defining the scope, essentially what we're going to model. In traditional threat modeling, this is often an entire application or system. We then create a graphical representation of the system, drawing all the components and how they interact with each other. At this stage, we also identify trust boundaries, the other points where the level of trust changes, in particular, the level of trust of data. These are often data ingress or egress points. For instance, data coming from a user into the system, or data going out from the system to a third-party service. We then continue by enumerating potential threats for each component of the system. This can follow a structured technique like STRIDE or PASTA. After threats have been identified, we then proceed in evaluating them, understanding if there are already compensating controls in place, and assigning a risk rating which can be used to prioritize threats for mitigation. And as part of risk mitigation, we identify potential countermeasures for each of the threats that have been identified. We then create a summary with the identified threats, risk rating, and mitigation strategies. We should also update the threat model periodically when the system evolves or new threats emerge to verify that the threat model is still current. It's worth pointing out that to create a diagram of an entire system or application, we typically need the assistance of several people, such as development leads and architects. And to help us identify threats, the application leads and architects are often joined by colleagues with specialized security knowledge. Traditional threat modeling presents some challenges. In particular, it can be difficult to scale threat modeling within the software development lifecycle. If we look at traditional threat modeling processes, as we said previously, the scope is often the entire system or application, meaning we need to involve a number of senior people that know about the architecture of the entire system. These are usually very busy people, and to model an entire application, we probably need them for at least one session lasting several hours. This is difficult to arrange, and it limits our ability to update the model periodically. Also, scoping an entire system typically results in modeling a simplified version of the system due to time constraints without many details. And this in turn can provide very broad results, which may be difficult to action. The activity of threat enumeration is typically performed with the help of the security team, whilst the average developer is rarely involved with threat modeling. So the first problem is really about scoping too broadly. The second is that we typically need security experts to help identify potential threats. This is because developers and architects may lack the mindset of an attacker, so it can be hard for them to come up with abuse cases. This reliance on security experts results in bottlenecks, limiting the scalability of threat modeling, particularly in fast-moving environments, and often results in only high-profile projects undergoing threat modeling. Overall, the traditional threat modeling process is resource-intensive and may be of limited value, as it is often performed after the application has been built, generating a large number of potential threats. Furthermore, by performing threat modeling at this late stage of the game, there are often limited resources available to remediate threats without affecting time to market.
Thank you, Andrew. So we learned from these initial slides that threat modeling has all the potential to be a very important activity. However, because it allows to identify threats early in the development process and incorporate the right security measures from the start. However, in the current form, it has a few problems. As Andrew said, it's very resource intensive. It often fails to produce results which are actionable, and also requires deep security expertise. So to address these problems, we developed a rapid threat modeling methodology aimed at developers. The methodology is tool-agnostic, so it can be implemented using both open source and commercial threat modeling solutions. So let's talk about scope. Instead of modeling an entire system at once, we model its system by decomposing it to components and then modeling the individual components. So with a reduced scope, we can go deeper with the analysis and produce results which are more relevant and actionable. Also, a scope like a component or a functionality can be modeled by the team of developers that is responsible for that functionality. So without the constant need to involve the application leads at every stage. And then further, to reduce reliance on security experts, we developed collections of threats and controls for different contexts. And we call these collections threat templates. So threat templates are really the core enabler of this methodology. They are predefined collections of up to 20 threats together with their corresponding controls. And each collection is geared towards a specific context and stakeholder. We have the implementation threat templates. These are usually suitable for an audience like developers. And they come, we have threats that come from resources like the OWASP Top 10 or language-specific secure coding guidelines. We then have the threat templates that belong to the deployment environment. So where is this component running? Is it running on AWS, on Azure, on GCP, on-prem, on embedded device? Based on these, we will have a collection of different threats. And typically, the stakeholder for these threat templates is the DevOps engineer or the cloud engineer. Then we have the compliance standards that the application needs to comply with. Examples of these are maybe PCI DSS for payments, HIPAA for health data, GDPR for PII, and many more. So typically, the stakeholder for this threat template is the risk owner of the application. Then last but not least, what we call organizational priorities. So these are the patterns of vulnerabilities that we see more recurrently within our organization. So these are the top risks that we should always have our developers to think about every time they're building something new. So threat templates really act as a checklist for developers to identify the most important threats for a given context without relying on security experts for the enumeration. So for each threat, including the template, we provide a description, default severity rating, and a list of applicable controls. We can also have multiple stakeholders work on the same threat model using different threat templates. I'll give you an example. We have a money movement application written in Java, deployed on AWS. We could have the development team to use the secure code implementation threat template. The cloud engineer would use the AWS threat template. And then since the application also is in scope for PCI, the risk owner would use the PCI DSS threat template. So with this approach, we have the added benefit that each of these stakeholders is actually an expert in that domain. And we have them focus just on the threats that are relevant for them. The methodology comes with a number of example threat templates. So we'll share the link in the last slide. You'll have the full documentation with all the examples. But really, security teams within the organization should tailor these threat templates to align them to the most important threats for their organization. Doesn't go. Okay, so this is an example of 3 different threat templates on the top: secure code implementation, AWS, and PCI DSS. So for each threat, we include a description, severity rating, and a list of applicable controls. Each template usually includes up to 20 threats. Here, we're just listing a couple for each threat template, just for a reason of space. But again, you'll find the full example of the methodology. Threat templates are made or tailored by the security team, but then are used by developers to focus just on the most important threats. Again, you'll find a chapter on how to build threat templates that are effective. I just want to spend a couple of words on these. So a threat template is used by developers, DevOps engineers, cloud engineers, architects, risk owners. But these profiles, they don't have the security knowledge to build a threat template from the start. So that's a job for the security team within the organization that should tailor threat templates and align them to the technology standards, compliance, and also the organizational processes. We recommend to focus just on the most important threats. That's why we hint at 20 as a good number, because in that way, the developer can quickly read the list and understand it. We don't want to be exhaustive. We don't want to create a threat model with hundreds of threats then become just noise. We want every developer, every time they're building something new, to focus on the most important threats for their context. And we can start creating threat templates based on resources like PCI DSS, the CIS benchmarks, the NIST cybersecurity frameworks. And then threats can be mapped to the controls that we can find in the NIST special publication 853. So now let's take a look at the phases for the rapid developer-driven threat modeling methodology, or in short, RaD-TM. So we start by creating a graphical representation of the functionality. We map its components, how they interact with each other. Then we identify trust boundaries. So we want to highlight points in which the level of trust in the data changes. For each component, we then enumerate potential threats. And we can do this by applying one or more threat templates. Then, based on the threats that we have identified, we can map the corresponding controls, and then we evaluate whether the control has been correctly implemented or not. And based on this, we can update the status of the overall threat and understand whether or not it's remediated, unmitigated, or we can accept its risk. So now I'll walk you through an example to show you how the methodology works in practice. So first, we talked about scope at the start of the presentation when Andrew was reviewing the challenges with traditional threat modeling. So with traditional threat modeling, we often try to model the entire system at once. So this involves involving many stakeholders, so very difficult to do at scale. And also modeling the entire system is actually difficult. Typically, we end up modeling a simplified version of that system, which in turn produces results which are vague and very far from being actionable. With RaD-TM, we shift towards like a feature-based threat model. So with a reduced scope, this allows us to go deeper with the analysis. And then a more focused scope that is focused just on components or functionalities can actually be modeled by the team of developers that is responsible for that functionality, which makes the exercise easier to repeat within that development team, also to keep the model up to date. Where do we start? So if we have a big project, we need first to decompose it. So we need to identify all its key components and the teams that are responsible of developing those components. Then for each of these components, the security team can work with the development team to identify the key flows. So really, what should be threat modeled? Which threat templates should we use for the model? Then the development team that is responsible for each of the flows builds the corresponding threat model. And then we can link all the threat models across the components together to get an overall model of the entire system. So each threat model can then be kept up to date by the relevant teams that use it as a proactive exercise every time they are building something new. So now let's analyze how this works by analyzing a specific functionality. So here we have a money movement application. This functionality allows users to transfer funds between the accounts. The application is hosted on AWS in scope for PCI, written in Java. So we first note down the inputs and outputs of the system, the high-level flow of the functionality, and these are information that are typically included in the development story. So things like your Jira tickets. And from here, we create the graphical representation of the functionality with the different components, how they interact with each other. And since we are focusing on a specific functionality, this can be modeled by an individual developer or a small team. So in this example, we can see the traffic flowing through the load balancer, hitting the Java application hosted on ECS. This is also interacting with the payment service hosted on Lambda, and they both interact with the MySQL database that is hosted on RDS. At step 2, we draw the trust boundaries. And a trust boundary is a point where the level of trust in the data changes. So this methodology is designed for developers. So again, we want to keep this simple. The objective is really to separate trusted with untrusted systems. At this point, if we have the need of nesting multiple trust boundaries, it probably means that the scope that we selected is still too broad. And probably we need to take a step back and decompose the components further. In this example, we identify a public network and 3 internal VPCs. So these become 4 different trust boundaries that we can see here in dash red. So each data flow that crosses one of the trust boundaries, then we should consider that data with a different level of trust. In step 3, we identify potential threats. So we do this using 3 different threat templates. Here we're modeling a Java application that is hosted, as I mentioned, on AWS and is scoped for PCI. So we look at the first table. We now have the first stakeholder, it's a developer, and they use the secure code implementation threat template. So this developer is concerned about an insecure direct object reference risk either, because internal object references of the application could be manipulated, allowing an attacker to access data unauthorized. So the default severity for this threat is high. The developer also considers SSRF as a potential risk for both the Java application and the application load balancer. We then have a second stakeholder. This is a cloud engineer. They use the AWS threat template, and they review the model and identify there could be a misconfiguration of the S3 buckets. And this could allow, again, unauthorized access to the data, pose a risk from both confidentiality and integrity to the data that the application consumes. By reviewing the model, they're also concerned about an insecure VPC configuration, which could potentially fail to offer the level of segmentation that is required by a money movement application. The third stakeholder is the risk owner. So they review the threat model from the perspective of compliance to PCI DSS, and they are concerned of a potential unauthorized access to cardholder data. These noise in particular, the concern is in particular for the back office flows. If exploited, this could provide unauthorized access to cardholder data, which is very bad from a PCI DSS perspective. Another issue is about data retention. So as per PCI DSS, data should be discarded after a certain period of time. So the risk owner here is concerned that there is no data retention policy in place. So this could be a problem for the application. So each of these stakeholders is an expert in their domain, and given the scope is focused on a specific flow, they're able to pinpoint the right threats, leveraging the appropriate threat templates. As I mentioned earlier, each threat template has 20 threats. Here we chose just a couple as an example on all three threat templates, but then you can find the full example in the logi, and we'll share the link in the last slide. So at step 4, after we have identified the threats, now we map the corresponding controls, and also we note down whether the controls have been implemented or not. So the IDOR is actually compensated because we have comprehensive authorization checks. So they're implemented at every layer together with randomized references. So we can consider this control as implemented. We can put a yes in the control implemented column. The SSRF also is correctly mitigated at load balancer level, but the Java application does not really validate inputs when building requests to internal URLs. So we'll need to enforce proper input validation at the application layer when building internal requests, and we can mark these as partially implemented. Then we have the AWS engineer reviews the blueprints for the VPC configuration. They confirm that the segmentation is properly designed between the VPCs. Security groups are correctly configured in the design plans, and also VPC flow logs are already planned. So finally, the risk owner confirms that the access control to cardholder data are actually correctly enforced and monitored, while a data removal mechanism exists for cardholder data and PII, but doesn't exist, it's not even planned for the application data, which is stored indefinitely. So probably this will need to be included in the recommendations. So we now review the threats, and based on the control implementation status, we can update the overall status of the threat, and we can also amend the severity rating. So amending the severity rating is optional. It really depends on the skill set and responsibility of the stakeholder. We can also leave the default severity rating that we find in the threat template. So the IDOR is mitigated. For the SSRF, we can keep the severity to moderate. And for the VPC configuration and the authorized access to cardholder data, these are mitigated as well. The data retention issue, we can change it from moderate to low, given only the application data is stored indefinitely. That's not really part of the scope for PCI DSS, so this can also be marked as accepted. So we can now put everything together. We can annotate the threats from the different threat templates on the diagram, and we can have a summary list of all the threats. We can use the severity rating as a way to prioritize our remediation efforts.
One benefit of shifting the activity of threat models to developers without relying on security experts is that more threat models are created. This in turn frees up the security team, who have more time to review the threat models and to do other things. In this way, we can create an asynchronous process in which we're able to decouple who is building the model from who is responsible for reviewing it. If we implement this process, then we can actually begin to scale threat modeling, even in large or fast-paced organizations. The methodology we've described provides a lightweight approach to integrating threat modeling within the SDLC, focusing on modeling individual functionalities and reducing reliance on security experts. Threat modeling can scale even faster when paired with automation, with generative AI giving us an incredible opportunity to implement this. For example, we can automate model drawing, making this time-consuming process much faster, and then integrate the model into development workflows such as Jira, enabling continuous refinement of the model as components or flows evolve. We can also automate threat enumeration by selecting threat templates, depending on the context, and then mapping the corresponding controls. This allows us to standardize both threat enumeration and controls within our organization, focusing on the most important risks and helping to ensure compliance. To conclude, to set up a scalable threat modeling process, we need to start by developing or training our development teams on lightweight threat modeling techniques, shift from threat modeling an entire application to delegating the threat modeling of individual components or flows to the development teams. We need to provide standardized lists, like the threat templates we've described, so that developers can identify the most important threats to their organizations and can incorporate security controls. Development teams should create the models, and security teams can then review them asynchronously. And lastly, where possible, we should provide developers with automated tools to reduce manual overhead. As promised, you can review the full methodology paper alongside 3 example threat templates online. We encourage you to try this out with one or more friendly teams in your organization and provide us with feedback to improve the methodology. You can also contribute threat templates yourselves. We're planning to create a collection of publicly available threat templates that can be used on demand and fine-tuned as needed. Thank you for your attention.
Wonderful. Thank you very much, Andrea and Andrea. I think this is a much needed project because every single team I meet who wants to do threat modeling, question number 1 is, where do we start? Right, and give me an example. Has someone done something like that before? Right, and I think it's great that now there's this methodology. So are you doing threat modeling? Do you have any questions on threat modeling? Yeah.
I have a couple, actually. The prioritization, how do you get your developers on what to prioritize and how? Because you give them 20 threat templates, how would they know? Is it IDOR or SSRF? Or which of those, how would they know? Because what developers will do, they work on 2-week sprints. So which of those do they put first? That's what I was thinking. Like, how do you get prioritization in that methodology? And how do you get, do they do the infrastructure? How do they know if this mitigated further up the chain? So no. That's some of the links that I was thinking, how would the developers do that if they're in their own little confine?
Okay, sure. No, that's a great question. So probably, the second, let me answer the second part first. When you say, like, what if that threat is already mitigated at platform level? So that's really, how the threat template should be built. So for instance, you have a cloud application, you have an application, it's deployed on AWS, you already have a number of controls at platform level that mitigate some threats. Those threats should not be in the threat template for start. So the infrastructure people, they should not even look at those threats because they're already mitigated at platform level. The developers are given the threat templates, they don't really build it. So for instance, we run this with organizations and they have threat templates that are separated among developers, infrastructure people, risk owner, and other profiles. And of course, there is prep work on creating the threat templates. So they don't come like you don't just use the default ones. You need to adapt them to what your platform is already protecting you against, at which layer you are deploying that application. So you wouldn't be using 3 threat templates in the entire organization. It really depends on the product team. So what we see is actually, each product team, usually they have slight variations of threat templates. Some of them, they don't even get to 20 threats. Now they as you mentioned earlier, how do you make developers choose, okay, this is an IDER, this is an SSRF. So they don't. They really match all the different possibilities. So we get them, they are developing a new flow. They match all the threats that the security team has chosen for them, and they think at design phase, do I have controls against those? And if the answer is no, then they do further investigation in understanding whether the control has been designed or not. And then that is done in the design phase. So even before they start developing.